we finished chapter 1 last week, so let's do chapter 2. Okay. Motion in 1D. Okay. In one dimension or 1D. Okay. Okay, let me make it a little bit smaller so that okay. Okay, good. Okay, so last week is our first week, so we kind of we went through the some basic introduction for this class, kind of give you the big picture of what physics is and what kind of physics we know, and also went through some basics in chapter 1 about units, a lot of stuff about units like fundamental quantity, derived quantity, and the unit conversion. And we also talk about something about numbers like sig figures and how many digits to keep in your calculation, and also math you learned before like arithmetic, algebra, trigonometry. Now there is a part that's in chapter 1. It's called vector, but we didn't, which we don't talk about. We actually postponed this part to chapter 3 when we start to talk about 2D motions. I think because we don't need vector for 1D motion mostly, and we do need to know the concept, but we don't need to know the calculation. So my experience is better to kind of postpone a little bit. So anyway, we're done with chapter 1. So remember that's this one week actually corresponding to 2 weeks in our in normal semester, like in the fall or the spring. So we're kind of finishing this one chapter by 2-week lecture time. So we're gonna speed up a little bit this week. I think we're gonna definitely finish chapter 2. We might start chapter 3 a little bit as well, because I want to start slow, but because we have certain material to cover, so I also want to make sure that we can get to where we want to be. So anyway, so we do chapter 2 now. Okay. I mean, hopefully you guys already finished your chapter 1 homework and submitted your answers on website, because that due date is Sunday night, right? So same thing, you could start to work on chapter 2 homework from today. Okay. So what is the subject here? So starting from this chapter, we actually start to do our going to actual reaction, actual actions. So it's basically we're going to start learn serious physics here. Now remember, our subject in this whole semester is mechanics, right? And mechanics is actually to study motion. Okay. So motion is our central topic of the whole semester. Now, what do we want to start? There's all kinds of motions in our everyday life and in this world, right? But basically, like whenever you're running, like walking, running, driving in a car, or you see something, you know, like stone moving or whatever, things moving around you, that's motion, right? So the question, which kind of question we should we start to look at first, right? Now, it turns out there's two type of questions you can ask. Roughly, the first type is question what. Well, the second kind is question why. Okay. Now, in the specific case, this question meaning that how do we describe a motion? What kind of quantity we specify so that we have a good description of motion, right? So this is called describing a motion. And the second kind is like after we know how to describe a motion, how do we explain a motion? Why in the specific situation we have this kind of motion rather than another kind of motion, right? What determines the motion, right? What determines the behavior? So this is a kind of explaining. A motion, okay. So these are our two topics, like important topics for the semester. So there's a name for this is called kinematics. And this is called dynamics, okay? So we're gonna spend chapter 2 and chapter 3 on this topic, and then chapter 4 on this topic, okay? This is Newton's law. Chapter 4 is Newton's law. We'll start from describing the motion, and then after that, we'll go to explaining the motion, okay? So that's where we're gonna start, okay? Now, another question, what kind of motion should we talk about when we discuss this issue, right? Discuss this kinematics issue. Well, again, we have a lot of choices, right? There's a, because we have all kind of motions, but actually, almost as a rule in physics, we always start from cases that are the simplest, okay? After we understand the simple case, we'll then go further to more complicated case. Okay, I guess this is not a surprise because most classes we take, like starting from our elementary school, goes like that. For example, in math, right, we always start from the simplest math topic, which is like numbers and counting, right? And then we do addition, subtraction, and then we go multiplication, division, and then we go to algebra, right? We do like more and more complicated things as we go along. Same thing. We start from physics. We start from simplest case possible, which is as you can imagine, the simplest case, the simplest kind of motion we have is going to be motion in one dimension. Okay, so that's why we start from this topic here. Okay, so what is motion in one dimension? Okay, basically it's very simple. So draw, for example, suppose you draw a straight line here. Okay, okay. Now let's say there's an object on the line. Okay, it could be a dot or it could be a car or whatever. Now, as the car moves, because it's a motion in one dimension, so it basically have to stay on the line. It cannot go off the line, right? So the choice of the motion is kind of limited. Pretty much the object can go either forward or backward, you know. There's only these two directions they can choose from. Well, when it goes one direction, right, it can go all kinds of, but still, there's still kind of a different motion you can have, even for the simple case, as we will see in a little bit, okay? So you may feel like this is too simple, but actually it is not totally unrealistic. There's one kind of motion that we do almost every day, you know, it's essentially a one-dimensional motion, okay? Can any of you give me an example of one-dimensional motion that happens in everyday life? No? What kind of motion we have? Like we're going on a straight line, you know? Okay, I got a message here. Okay, let's see. Car. Okay, car. Yeah, definitely. See, that's a very important kind of a one-dimensional motion, right? So when you drive on the road, right? Mostly you're driving on the straight line, you know, like this. You don't want to go off the line, right? If you go off line, it's dangerous, you know. You go to a different lane, you know, like going like this, you know, it's going to be not good, right? For your safety and for other people's safety. So yeah, it actually the motion of the car mostly is a one-dimensional motion. So again, this tells you, like, when we're learning physics, what we learned here is nothing. I mean, it's not like something mysterious or something really high level, really complicated. We're learning something from essentially from our everyday life. You know, the only phenomena we have are, okay, there's another message. Oh, somebody's saying, oh, it's forever to everyone. Welcome to OKC, where we drive in 3D. Well, that's too much. I mean, I don't think you can drive 3D. Well, 2D is probably the most. I mean, I don't think you can fly, you know, or going into the ground. So probably the best is 2D. But anyway, okay. So again, so the subject mechanics, right? Because we care about motion, so it's actually coming from our everyday life. There's a lot of intuition goes in there, and most of the intuition we have, I mean, about mechanics are probably correct. You already developed those intuitions because you've seen these motions, you're experiencing these motions every day, you know. So now the next thing we want to talk about is what kind of quantity do we want to do to describe this, want to use to describe this motion, you know, like see here. So again, I'm going to ask you guys, what kind of things you think which can be used, what kind of quantity, or you may already know, you know, from your experience that can be useful to for describing the motion. If you want, you can send me a message, you know, or you can just talk, you know.
Do you mean the speed?
Speed, definitely, yeah.
Distance?
Speed, distance, okay, good. Speed, distance. Anything else? Okay, I got a message. Okay, direction. Okay, direction is definitely useful as well. Direction. Anything else? Okay, how about time?
Is that not implied with speed?
Well, it is, I guess time, you can say time is included in speed, right? Because when you say speed, there's times in there, but time itself can be useful, right? Not only connected to speed, right? For example, you may want to know how much time it takes for you to go from one place to another place. Well, you can say the same information using speed, but still time is something that you can think about, right? And there's actually another one, it's called acceleration. Well, this one is not as common as the other ones. I mean, from your everyday experience, unless you're kind of people that really like a fan of like muscle cars, you care about how fast your car can speed up from 0 to like 60 miles per hour, you know, things like that, you know. Well, certainly you have like a bigger engine, you know, like more powerful engine, your car can speed up faster. Well, in that case, essentially you're talking about acceleration, right? Well, or some people, if you're like a fan of like space traveling stuff, you know, when the rockets start to launch, right? There's a huge acceleration, and they talk about like in terms of G numbers, like 1G, 2G, 3G, or something. Actually, when we went to Disney World, there's a ride called like a mission to Mars or something. They kind of simulate the rocket launch. Okay, in that case, they can get to like 2.5 G. I feel very uncomfortable. You know, it feels like something's pressing on you. You know, like it's really hard for you to move and everything. But anyway, I heard that for Saturn V, when they go to the moon in 1960s, the rocket can get as high as like a 5G, you know, like that. When we talk about that, that's all like acceleration. Okay, we're gonna talk about G and acceleration later, a little bit later. But anyway, so these are quantities we we use to describe the motion. Okay, again, as you see here, right, they're not something mysterious. They're not invented by some genius. This is something we use every day, right? So let me talk about them like one by one, following some order. So we'll start from the first, the most important one. Like let's start from time. Okay. This is our one of the 3 fundamental quantities. So we kind of already know a little bit, and also we have a lot of experience with this, right? So here, I only want to specify like a difference between 2 concepts. Okay. So when you talk about time, we use T for that. Okay. You can talk about 2 things. One is a moment. Okay. Another is an interval, okay? And these 2 are different, okay? So for example, for moment, we say this is like T, let me say, normally we use like a TI or TF or T naught, whatever, you know. Well, for the interval, it's actually equals to the difference between 2 moments. For example, TF minus TI, okay? And this is defined as delta T, okay? So this delta here is a Greek letter. It pronounced like delta, okay? So in physics and in math, this symbol is normally used to describe a change, okay? Delta T means change of time. So change of time is like give you interval. for example, like for the moment, right? Like this class started at 10 a.m. in the morning, right? That 10 a.m. is a moment, okay? 10 a.m. It's like a point, right? It's like an exact time. Well, an interval would be like a period of time. For example, this class starts from 10 and end at 11:15. So the period would be from 10 to 11:15. And that's, if you use 11:15 minus 10, you got actually 1 hour and 15 minutes or 75 minutes, right? So that's the period, okay? That's like an interval in time, okay? So sometimes you can draw everything on a straight line, like a axis, time axis, right? Now a moment would be represented by a point on the line, while an interval will be represented by like a distance between the 2 points, like this, right? This will be your interval, right? Delta t, okay? Now again, remember we use second as our main unit for time. We also have minutes and hour, et cetera, okay? We're good? Okay, so let's go to the second one, okay? The second quantity I want to talk about is actually related to distance and also to direction. Let me move this this way, okay? Okay, they are called, it's called displacement. Well, distance is actually related to it. So let me write distance here and the distance, okay? So to talk about these, let's start from something called position, okay? This is actually, we use X for position, okay? This is kind of similar to a moment in time, okay? So for the one dimension line, we talk about a position of something would be just like a point, okay? Well, you can define an origin here. Well, the position of the object will be described by a single coordinate on this axis, right? You can label this by X or XI or whatever, okay? For example, this might be at 3 meters. That's a position of the object, okay? Now, what is displacement? A displacement is kind of like a time interval. It's an interval of in space, okay? It's defined as delta x, so change of the position. So this is equal to xf minus xi, okay? For example, this may be here, okay? Xf. Let's say, suppose this is a 7 meter, okay? So what is the display? Okay, let's say the object goes from one point to another point. I here stand for initial. F here stand for final. So you have objects starting from the initial position going to the final position. So the displacement of this motion based on according to the formula is, you can calculate is 7 meter minus 3 meter. So that's 4 meter, okay? So the displacement of this motion is 4 meters, okay? Now, what about, let's do another one, okay? Let's say, what about you start from 7 meter and then you end up with 3 meter. What is the displacement in this case? Anybody? You can send me a message if you don't want to talk. No. Just use the formula to do the calculation. Go ahead.
Would it not just be 4 meters?
Say it again.
Would it not just be 4 meters?
4 meters, okay, not quite, okay. Remember definition here, right? You need to take the final position minus the initial position. So in this case, the final position is 3 meter, while the initial is 7 meters. So 3 minus 7 is -4. So actually you got -4 meter, okay, for this displacement. As you see here, sometimes you got positive numbers, sometimes you got negative numbers, okay? So they're not, I mean, well, when you get, okay, somebody gave me, okay. So when you get negative number, there's nothing wrong, okay? So actually there's a meaning for the negative sign we got here, okay? So when you got positive, right, because we defined the positive direction to going to the right. So when you got a positive number, that simply means that your motion is going along the positive direction. So you start from 3, end up at 7, so that's going this way, right? Well, when you got a negative number here, that simply means, right, because you start from start from 7, right? You're going to the 3, right? So you're actually going to the left. You're going to the negative direction. So this minus sign simply tells you your displacement is going to the negative direction. In this case, going to the left. Okay, so there's a meaning for the sign here. Okay, there's nothing wrong to get a negative number for your displacement. This whenever it's positive, it means going along the positive direction. Whenever it's negative, it means going along the negative direction. So as we see here, this concept displacement, it actually containing two parts of information. It contains information about the distance traveled, but it also tells you the direction traveled. Yeah. So because of this reason, this displacement is actually a better quantity to look at. I mean, in some cases, okay, than distance, because it gives us both the information about distance or length and the information about direction. Okay. And actually, this is our first example of a vector, you know. So we define this as a vector. We call displacement is one kind of vector. Well, vector, so maybe let me cross this here. So what is a vector? A vector is something that has both a magnitude and a direction, okay? As I said, we're going to talk about the calculation on vectors operations more in depth in chapter 3. Well, but it's good to get to see this concept first, okay? In this chapter. So vector defines something both at magnitude and direction. Displacement is our first example, okay? Well, in comparison to that, there's another kind of quantity called scalar, which is defined as something has only magnitude. There's no direction of it. Okay. Magnitude. The eraser of this one is not working, so let me magnitude. Okay. So the displacement is our first example of a vector. Well, correspondingly, distance here is a scalar because only care about magnitude. It does not care about direction. So for example, you when you go from one place to another, sometimes you may not care about the distance, the direction, but you just simply care about how far it traveled, right? Like 60 miles or something. Because for filling your tank, right, of gasoline, it doesn't matter which direction you travel, right? What mattered is how far this thing is, because that determines the gas number of, gallons of gas you use, right? So in that case, we have a scalar. So anyway, so this is the difference between the two cases, okay? Okay, again, if you have any questions, please stop me and then, or you can send me a message, okay? So the next one we want to talk about is acceleration, okay? No, I'm sorry. Speed and velocity, okay? So in this case, we'll talk about velocity, okay? Which is related to speed, but velocity is a little better quantity to look at. So what's the definition of velocity? So if you start from displacement, a velocity is simply defined as displacement divided by a time interval, okay? So delta x divided by delta t, that gives you velocity. So you can write like explicitly like xf minus xi divided by tf minus ti, okay? Okay, so again, that's a very familiar quantity to us because it's very natural for us to use velocity or speed to describe the motion, right? It tells you basically how fast we go, right? See, because it's a ratio of the displacement divided by the time change, right? Certainly, if the time change is really small for the same displacement, the smaller time change you have, the faster, the bigger the velocity will be, meaning the faster the object is. And for the same time interval, the bigger the displacement, the bigger, the faster velocity again, right? So it's kind of very natural way to describe how fast the object moves. And let me give you an example, right? For example, in this case, let's say for this case here, let's say the time it takes is 1 second, okay? Now you can easily calculate the velocity there by using this definition, delta x over delta t. Well, the displacement is 4 meters, the time is 1 second, so the velocity is simply 4 meters per second, okay? Well, similarly, you can do this for this one, right? Let's say, again, delta t equal to 1 second, velocity would be, maybe let's say, let's put it like 2 seconds, okay? So this will be given by this, but the displacement is -4, and the time is 2 seconds. So you got -2 meters per second. As you see here again, when you calculate velocity, it's possible to get a negative number here, okay? Why? Because certainly the displacement here can be positive or negative. Well, the time interval is always positive, right? Because the time cannot go back, right? It's always going forward. So that tells you the velocity certainly can be positive or negative, right? But this also tells you velocity is this quantity that we just talked about. It's a vector because it has both magnitude and direction. This negative sign here, sorry, there's an equal sign missing. The negative sign here simply tells you the object is going along the negative direction, just like displacement, okay? So the sign of velocity has a clear physical meaning, just like it's the same meaning as the sign of displacement. It simply tells you which direction the object goes, okay? And also you see from here, this is 1 second, 2 seconds. The distance traveled are the same, but since this one traveled in a very smaller time, so the velocity is larger than the second case when it travels with a longer time. It's same distance. So speed actually is so velocity, because it has both magnitude and direction, right? So this quantity here, speed, is just tells the magnitude. So velocity is actually a quantity that has both speed and direction, okay? So meaning that the speed itself is a scalar. It only has magnitude. Again, when you're driving, right, you can check your speed on your speedometer. That's always a positive number. Is 30 miles per hour, 50 miles per hour, whatever it is. But this number is it's always positive, meaning that there's only magnitude in there. You never care about the direction you go. On the highway, either way, right? You go, if you are going above the speed limit, you may be pulled over, right? You get a ticket because you're violating the speed limit. When in the speed limit, nobody cares about which direction you go, right? The only thing is like how fast you're going. So it's basically the magnitude of the motion, of this velocity. Well, this velocity concept itself includes both speed and the direction of this motion. Okay. Any questions? Okay. Now, by the way, we notice again, the displacement is a fundamental quantity, right? Because it's just essentially just a length. So it has unit like meter, right? But the velocity here is not a fundamental quantity. And then the units given by meter per second, because by definition, we have a length divided by time. So it's meter divided by second. So it's give you meter per second. We already talked about the unit of speed in our first, chapter 1, but here you can see again, we can simply use the fundamental quantities and their units to derive new quantities, new units for new quantities, okay? Okay, let's go to the next quantity, okay? Acceleration. Okay. Now, as I said, this quantity may not be as familiar as the other quantities we talked about so far. So we will spend a little more time on this one. Okay. So let's start from the definition. So normally people use A for acceleration, as starting from the first letter of this word. So acceleration is defined as this. Okay, delta V over delta T. You can write like VF minus VI divided by TF minus TI. Okay. So that's what it means. Okay. Now let's look at the unit. Okay. So because velocity, the unit for velocity is meter per second, and then unit for time is another second. So the meter per second. So you can write like meter per second squared. Okay. So the unit for acceleration is meter per second squared. Okay. We can derive from this definition here. Okay. And before we go further and try to understand the meaning of that, let me ask you a question. What do you guys think? Is acceleration a scalar or is a vector? You can send me a message, okay? Just send a message to me. Okay, let's see. Okay, I got one
Yes.
response. Other, anybody else?
Should be a scalar, right?
It's a scalar. Why?
Because it's, I mean, I don't know.
Okay, I got a couple of response saying it's a vector. Actually, it is a vector. Why? Because for our remember the definition here, right? A vector has something both magnitude and direction, right? A scalar only has magnitude. Now, does the acceleration has a magnitude has a direction? Well, look at the definition here, right? As you can imagine, right? In our case, it's one-dimensional motion, so you have something that can be positive and negative. That means it has a direction, right? So in this case, this is determined by final minus initial. So if the final velocity is larger than initial velocity, you get a positive number for acceleration. But if it's if final velocity is smaller than initial, you get a negative number. So it means like the acceleration can be positive and negative, just like displacement and velocity. So it's a vector. Okay. Well, in this case, there's no special name for the magnitude of acceleration. Like in the case of displacement or velocity, we had the word like this distance or speed. In this case, we don't have those. We just have this name for this whole thing, the vector. When we want to talk about the magnitude of acceleration, we just say magnitude of acceleration. Okay. As you can tell, when you drive your car, there is no a meter that shows the acceleration of the object. Okay. Well, there is one for the revolution per minute, like how fast your engine runs. You know, well, that's kind of related to the acceleration. When you press the pedal, gas pedal, the revolution, the RPM normally goes up. The engine starts to run faster, and then you normally have an acceleration visit, but we don't have a direct measurement of acceleration on your car, so you don't really know the acceleration there. This is not really very important for us either, because normally the acceleration is not too big. You know, it never get close to 1G or something. So, so it's not too bad. So anyway, so this is this new quantity. Now let's try to understand a little bit of the physical meaning of this quantity. Okay? Now, see, whenever you have something, right, we talk about these quantities. How do we understand the meaning of them? Well, for these quantities like time and displacement, they're simple, or distance, right? Because you kind of already have the intuition about it from your everyday life. Then what we need is define the quantity so that it agrees with your intuition. So it's that's not a problem. You kind of know what it is. But for some quantity like acceleration, you do not have a very good intuition, and then we have to define it first, and then kind of develop an intuition about it, right? So this is what is kind of making it hard. Now, how do we develop intuition about something so that we can feel this thing just like we feel about time or distance or velocity, okay? Now, there's a very useful technique here, okay? I want you guys to keep in mind, because for any other quantity we learn in this class, which are defined as a formula, you can use the same trick, okay? This trick is actually, to understand the meaning of any formulas, right? The trick here is, we can call it giving a example or giving examples. Okay. Okay. So see this thing here, right? It's totally algebraic, right? It's all symbols. There's no numbers, right? It look very abstract for you. You don't really know what it means, right? So to develop a meaning of it, you need to consider some specific examples. Okay. So let's do that. Okay. Let's say, for example, consider the time interval to be 1 second, okay? Let's consider two different motions. Let's say the first velocity change, okay? Let's say it's, okay, maybe let me be more specific, okay? So let's say in the first case, VI equals to 0, and VF equals to 2 meters per second, okay? And in the second case, VI equal to 0, and VF equals to 4 meters per second, okay? So let's try to calculate the expression of these two cases, okay? Again, very simple example, but it can help you to understand the meaning. So if you plug these in numbers, so we have VF minus VI, so it's 2 meters per second minus 0 divided by 1 second, okay? So the first case, you have 2 meters per second squared, okay? Or in the second case, if you plug in numbers, you have 4 meters per second divided by minus 0 divided by 1 second. So you have 4 meters per second squared, okay? So as you see here, in the second case, you have a larger acceleration, right? Now, what does that mean? Look at this, right? So that simply means that during the same time interval, the second case, the velocity increase changes bigger, right? See, from 0 to 4. Well, in the first case, from 0 to 2. So the first case, the velocity change is smaller than the second case. Correspondingly, you have a larger number for the acceleration in the second case, okay? So basically, hopefully from this example, you can kind of see the meaning of acceleration, right? It tells you how fast your velocity changes, okay? Now, if you look at this, the definition, it makes sense, right? Because see, the acceleration is proportional to the velocity change, okay? And there's also inverse proportional time change. So the bigger velocity, for the same time change, the bigger velocity change, the bigger acceleration will be, right? For the same velocity change, the smaller the time change, the bigger acceleration will be, right? So again, in both cases, it means that this quantity is you can use this quantity to describe how fast the velocity changes, okay? So in this sense, acceleration is kind of like velocity. Remember, velocity is something to help you to describe how fast the position changes, right? So the velocity, where's my mouse? I don't know. Okay, anyway, I will use this. So see, it tells you how fast the position changes, right? Because the position change, the displacement divided by the time. So an acceleration, in some sense, you can say it is the velocity of the velocity change. It's the changing rate of the velocity, not the changing rate of the position. The changing rate of position is the velocity itself. Well, the changing rate of the velocity is the acceleration. Did that make sense, you guys? Okay, so hopefully, again, okay, I see some thumbs up, good. Again, either because you guys are smart or because I'm a good teacher. So either way, it's good, you know. So this, again, as I said, this is not a very familiar quantity. So you need to use this kind of example to help you develop the intuition. So another thing I want to say here, because of vector, right? We want to kind of see, try to see the meaning of the direction of the acceleration. Well, the meaning of the direction, the displacement, the velocity are pretty clear because it simply tells you the direction of motion, right? But what about the direction of acceleration? it's not that direct. Okay, so let's try to again try to think about some specific examples. Okay. Again, kind of hard for me to draw this kind of a straight line on using the stylus. So let's consider one motion here first. Say you have an object here, I mean like a sphere or something, you know. It goes from let's say at the initial velocity here is vi equals to let's say 1 meter per second, and then vf equals to 2 meter per second. Okay, maybe let's start from 2 to 4. Okay. Now let's say another case. Okay. This case we start from same initial velocity, but in the end we got 1 meter per second. Okay. Let's say for simplicity, both cases the time changes 1 second. Okay. Now let's try to calculate the acceleration in these two cases. Okay. Using the definition here. Okay. The first one is simple because just plugging numbers, right? So final velocity is 4 meters per second. Initial is 2 meters per second divided by delta t, which is 1 second. This gives us 2 meters per second squared. Okay. 4 minus 2 is 2. 2 divided 1 is 2. Okay. Well, in the second case, we have 1 meter per second as our final velocity, and then 2 meters per second as our initial, divided by 1 second. So this gives us 1 minus 2 is -1, so -1 meter per second squared. Okay. See, what we got here is we have two cases. The first case we have a positive acceleration. The second case we have a negative acceleration. Okay, let's go back. Let's look at these cases, right? See what's happening here. Okay, in the first case, the initial velocity is smaller than the final, meaning that this object is speeding up. In the second case, the final velocity is smaller than initial, meaning this object is slowing down, right? And in the first case, you have positive acceleration. In the next, you have negative acceleration. So this kind of, you can see from this example, okay, the meaning of the direction of acceleration. Okay, notice in both cases they're going to the right, so the direction and motion are the same, but the acceleration has different signs, right? This one is positive, this one is negative, and you can see clearly in the first case it is positive because final velocity is larger than initial. Okay, in the second case it's negative because final velocity is smaller than initial velocity. Okay, that makes sense. So basically what we can conclude here is when the object speed up, acceleration is positive, and when the object slows down, the acceleration is negative. Okay. So this is the kind of you can tell the physical meaning of the quantity, right? Again, the direction is not directly related to the direction of motion, but kind of related to how the velocity changes. Okay, which makes sense because see, if you look at the formula here, right? If the final is larger than initial, you got a positive number here, so A is positive. If the final is smaller than initial, you got a negative number here, so A is negative. Okay. That makes sense? So, however, this is not the full story. Let me give you another example, okay? Another two examples, okay? Let's say, suppose this is a direct two one-dimensional motion we have, okay? Let's say, but in this case, let's say the object is actually going to the left, okay? So very beginning, the object going VI equals -2 meters per second. In the end, the object goes like VF equal to -4 meters per second. Well, the second case, VI equal to -2, VF equals to -1. Okay, let's try to calculate, again, try to assume that delta equal to 1 in both cases. Let's try to calculate, see which one has larger, I mean, what is the acceleration in these cases? Okay, let's call 3 and 4. So in the first case, right, using the definition, final velocity minus initial, you have 4 meters per second minus -2 meters per second divided by 1, right? So this is -4 plus 2, so it's -2 meters per second squared, okay? In the second case, you have final is -1, initial is -2, divided by 1 second again, okay? So that's -1 plus 2, so it's 1 meter per second squared. Okay. So what we see here is, well, in the first case, the actually negative, but see in this case, the object actually speed up, right? It's going to the negative direction, but it's speeding up, right? From 2 meters per second to 4 meters per second. Well, the second case, we got positive acceleration, but the object is actually slowing down. So it seems like different from what we conclude here. That's simply, well, there's nothing mysterious here. It's simply because this object now is moving to the left. So if you we want to summarize these two cases together, this first case and the second case, what we can say is this, okay? So when the object speeds up, object so A is the same, A has same direction as V, okay? When the object slows down, it has the opposite direction as V, okay? Now you can see that, right? See in this case, the object speed up, right? It's negative, but the velocities themselves is negative, right? So these are, well, it's going the opposite direction of the velocity, so it slows down, right? Well, same thing here. When A is larger than when A is positive, the velocities are positive, they speed up, right? Maybe let me put it a little better way. Maybe let me, sorry, let me write it a little bit differently. Okay? So when A has same direction as V, the object speed up. When A has opposite direction as V, the object slows down. Okay, so that's the, I guess that's the message, technical message here. But again, the point is not to kind of memorize these rules, but the point is to use the examples here to kind of help you to figure out the rule, you know? And you don't need to memorize this. Each time you're kind of confused about the meaning of the expression, you can just give it some specific example, just like what I'm doing here, you know? So that in the end, you got some numbers, I mean, some signs here, and you compare it with the signs of the velocities, and you can conclude the same rule as we're doing here, okay? So again, try not to memorize things, try to understand things, okay? Try to figure things out, okay? Do I have any questions? Okay. Well, we've introduced this, right? So we actually can go further than that, you know? For example, we can consider the change of acceleration divided by change of time, okay? We can define something like J, so-called J here, and then further on we can define delta J over delta T, and we can define something else, you know? We can continue this trend forever, okay? However, we don't do that in our class. We stop at acceleration. But as you can see here, right? Essentially, if you look at these quantities, they're not randomly located. They have certain pattern. There's certain way to organize them. Like the very beginning, we have this time here, which means basically that's a parameter that all motions depend on. Without time, you cannot have any motions. That's for sure. And then the basic thing you want to know about time is, I mean, the motion is how far it goes, right? So that's our displacement idea. And then after that, we want to know how fast it goes, right? How fast the position changes. We can define this like velocity, the changing rate. And then we go from there, we can define how fast the velocity changes. So that's another changing rate that gives us acceleration. And if we continue this trend, we can define how fast the acceleration changes, et cetera, right? So that's kind of the quantities we use to describe motions. Basically, to start from the distance or displacement and just describe how fast this thing changed and how fast it changed, et cetera, okay? So, so that's one way to kind of summarize it. Another way to see it is like, let me put them in a table, okay? So we've learned that there's two kind of quantities we have. One is called vector, the other one is called scalar, right? So let me put it in the table of all the quantities we learned so far, okay? So for example, first one, time is definitely a scalar because there's no direction for time or time interval, okay? T and delta t, they're scalars, okay? In some sense, you may say there is a direction, but there's never another direction. We always going forward, we never go backwards. So it's a scalar, okay? Now, then we have a displacement, delta x, that's a vector. Well, correspondingly, we have we call something called distance, which is basically the magnitude of displacement. Sometimes we use d for distance, okay? And then we have velocity, v, and then the magnitude of velocity we call speed. That's we sometimes use s here, okay, for speed, okay? And then we have acceleration, okay? That's a here, okay? We don't have any quantity here. There's no, we don't just specify, it's just the magnitude of acceleration, but we don't have a name for it, okay? This is kind of the summarize. Okay, maybe let me draw the other one, okay? So we have a delta x, and then we have a v equal to delta x over delta t. And then we have a equals to delta v over delta t, right? So displacement, then how fast this thing change, and then how fast this v change, et cetera, et cetera. So this is kind of another way to organize those quantities, okay? Do you have any questions? We're good? Okay, to describe motion, sometimes we use diagrams, okay? For one-dimensional motions, a very common kind of diagram is like this, okay? We will draw the time axis as the horizontal axis, and then the position axis as the vertical axis, okay? This is sometimes called a space-time diagram, okay? Because it gives you information about the position and also the time, okay? So let's try to think about what kind of a graph we can have for one-dimensional motion here, okay? First of all, let's start from something like this, okay? A horizontal line, okay? Yeah, I'm not drawing horizontal very well because yeah. Just think about this as a horizontal line, okay? I'm not drawing it as a horizontal, but it's horizontal, okay? Now my question for you guys is, if you have a motion, right, and then it's described by this horizontal line here, okay? What kind of motion is, which direction does the object go? Is that clear, my question? Does this object go into positive direction or negative direction or what? For this line, there's actually no motion, okay? Now, why? It is because, see, look at this diagram, right? So at the very beginning, this object is like here, right? As time goes by, the object is still here, you know, the object is always here. So that means the object is at rest, okay? This is at rest, okay? Okay, so again, what I'm doing here, again, I'm sorry, maybe my question was a little bit vague. I was trying to help you guys to kind of figure out the meaning of the diagram. So let's look at another one, okay? So suppose in this time, the object goes like this, okay? I mean, this is the diagram, okay? Now, which direction does the object go in this diagram?
Yeah, I think it goes positive.
One
Okay,
sec.
okay. Okay, positive. Yeah, positive is right. Yeah. Now, again, how do you figure out, right? So see, the object is like here, right? As time goes by, the object is actually going here, here. So basically it's moving along this line here, okay? So it's going, when time goes increasing, the object getting a larger position along this axis. So it's actually, this is a motion going positive direction, okay? Well, similarly, if you have a object, you have a curve like this, that means this object is going negative direction because as t increases, the object position of the object going down, so it's actually going negative direction. Okay, going negative direction. Okay, so another thing you can do here, you can actually figure out the slope. Okay, remember we talked about slope at the beginning of this class. Wait, no, sorry, x and t. So you have something like this, right? Say if you have a straight line, right? The slope of the line is calculated by taking the two coordinates along this direction. So let's say x2 minus x1 divided by t2 minus t1, right? Like this. But what is this thing? Okay. Well, this is simply delta x over delta t, right? Well, what is this? This is nothing but velocity, right? So the slope of this line on the space-time diagram has a physical meaning. It simply tells you the velocity of the motion, okay? That makes sense? So it has a physical meaning here, which is the velocity, because it's exactly our definition. So see, the geometrical definition of slope agrees with the physical definition of velocity. So the slope of this line here is nothing but the velocity, okay? Now, what do you have a more complicated motion like this, okay? Let's say you have something like this. Well, it's a curve, right? So it's not a straight line anymore. So, however, you can still talk about the speed, the velocity of the object. You can draw a tangent line of this object when it moves. Well, the slope of the tangent line gives you the speed, velocity of the object, right? As the object moves on the curve, as you can tell, the tangent line, the slope is keep changing. So the slope is changing. So it's not a constant velocity motion. The velocity is changing, but at any given point, the slope gives you the velocity. Okay. Now this part is a little bit complicated. We don't want to do a whole lot of calculation here, but I want to understand that the slope carries meaning in the more general case when you have curves and stuff. Okay. Let's stop right here. We'll continue tomorrow. We're almost done about the general definition of these quantities, like as we discussed. Just like a few more things to discuss, and then we'll give an example, like a specific problem to solve, and then we'll go to the second part of the chapter, meaning we'll study some specific kind of motions, simple motions on one dimension. Okay.